Alright, this is going to be problem number 54. On problem 54, what you're having to do is identify whether the sets of quantum numbers for a hydrogen atom are acceptable or not. So on A, you're given a quantum number of 2, a azimuthal quantum number of 1, and a magnetic quantum number of 1. And you have to figure out whether that's permissible or not. So what we absolutely need to know is that n is our energy levels. So n can go from 1, 2, 3, all the way up onto infinity. It can keep on going up. Alright, so now we get to the azimuthal quantum number. So since it's at 2, we know that the azimuthal quantum number goes from 0 all the way up to n minus 1. So since our n in this problem is 2, we know that for L we have 0 and 1. That's it. And then we have the magnetic quantum number, and the rules for the magnetic quantum number is that it's negative L, and then you include 0, and then you go all the way to L. Don't forget that there are numbers in between those. So we have to take our L. So for 0, we have 0. And then for 1, we have negative 1, 0, and positive 1. Alright, so now let's try and figure out what orbital this is. Let's not forget that 2 is the second energy level. L is the azimuthal quantum number, so 0 is S orbital, 1 is P orbital, 2 would be D, and 3 would be F. And then let's start writing this out. So we know we have a 2S, we know we have a 2P, and I want to think about these. These are the orientations. So that we know that for when L is 0, we have only one box, so who would have guessed? And when L is 1, we have 3 boxes. So this, and this are allowed, and this number, and this number actually describe the 2p orbital. Alright, now what we're going to do is we're going to get into letter B and see whether that is permissible or not. So now let's look at B, and B, we have n equals 1, we have L equals 0, and we have the magnetic quantum number equaling negative 1. Alright, so in this particular problem, what we have is we have energy level of 1. I know that in the first energy level that there's only the s orbital. So is this the s? Yeah, 0 for the azimuthal quantum number makes sense for s, but negative 1 doesn't make sense. Because if L equals 0, remember M, the magnetic quantum number, is negative L all the way to L, but you have to make sure that you do include 0. Well, 0, there is no negative 0 and positive 0. It's just 0. So that doesn't make any sense. There is no such thing. This orbital is indeed forbidden. Alright, let's do C. So on C for this problem, we have n equals 4, we have L equals 2, and we have the magnetic quantum number equaling negative 2. Alright, so 4. Alright, now L is 0 all the way up to n minus 1, so it would be 0 up to 3. So that is definitely permissible. And then I'm going to take L, and then I know L, since L's 2, magnetic quantum number would be negative 2, negative 1, 0, positive 1, positive 2. And since it's negative 2, and that's in the set possible, this is allowed. So what is this actual orbital? Turns out that this is the 4d orbital. Because remember L, 0, 1, 2, 3. 0 is S, 1 is P, 2 is D. So this is 4d, and then this first one we're dealing with, since it's negative 2, it's probably going to be dxy. That's my guess. Alright, so anyhow, let's now move to D. Now D should be quickly identifiable as forbidden. So there's n equals 3, we have L equals 3, and right there we know it's not permissible. We should, because remember, all the L values are based on n. So if n's 3, what are all the possible L values? Well, we know it's 0, 1, and 2. It stops there. Because remember, for L, it goes all the way up to n minus 1. So n being 3, 3 minus 1 is 2, L is not allowed. This is indeed a forbidden orbital. If you guys have any other questions, please let me know.